A question recently posed on the AP Calculus community was about finding arc lengths of generic curves in AP Calculus BC. And this video is going to show what I consider to be sort of the cleanest way without memorizing lots of formulas, driving at really what is at the core of the arc length formula, and showing how to compute an arc length of a curve in lots of different ways depending on how the curve is presented to you. All right, so we're going to start here with, in general, I've just got any kind of curve. And the big idea here is to realize that through local linearity, if you zoom in on any differentiable curve, ultimately, if you zoom in enough, that curve will begin to look linear, and not just linear, it will look like the tangent line at the curve at the point where you're zooming in. If I do that, once it becomes linear, and then like every curve is really just a series of these little linear segments, then I can find a length just using old-fashioned geometry, and I'm going to call this small piece of length dl, and it is comprised of a delta x and a delta y, a small change in x and a small change in y, which means my change in length is really just from the Pythagorean theorem, change in x squared plus change in y squared. Easy enough. So if I wanted to find the entire length of a curve, that would be just add up all of the little delta L's. If you then allow delta x to go to 0, so here's that limiting process again, then I can get an exact value for the limit. A sigma is really just a sum from some starting point to some ending point, wherever we happen to be interested in on the curve, wherever I'm starting to wherever I'm ending. And that square root becomes the infinitesimals dx squared plus dy squared, and I'm going to hold right there. This is what I consider to be arc length, and then what I turn that into completely depends on the context of the curve. So what we're going to play with here is the curve y equals x squared, and let's look from 0 to 3, and I'm going to solve that lots of different ways. So if x's goes 0 to 3, y's goes 0 to 9, and that's our fundamental context curve. All right. So what if I think about it just in the natural way of looking at things, y equals x squared? Well, I know this function is, this is currently a function of x. So I'm going to look at that integral of square root of dx squared plus dy squared, and I want to let my x values run from 0 to 3. But what do I do with this inside? Since my function is given in terms of x, I'm going to take this dx squared term and I'm going to factor that out. So in doing so, this becomes 0 to 3, x is 0 to 3, and when I factor out a dx squared, I'm left with 1 plus dy squared over dx squared times dx squared, all within the square root, which is equivalent to 0 to 3. Dx squared, dy squared over dx squared is really just 1 plus dy dx squared, and then when the dx squared comes out of the square root, it's just a dx. So this is really just 1 plus the derivative of y with respect to x squared. So that becomes 0 to 3 if y equals x squared, y prime is 2x, and this is the square root of 1 plus 2x squared dx, and that ought to give me the length of that curve. I'm going to put that on hold for a moment. I'll come back and calculate it in a second. The exact same curve I could also think of as x equals root y, and since it's in terms of y, I could say dx dy. Let's find the derivative of x in terms of y. That's a 1/2 y to the negative 1/2. So when I come back here and I want to compute the arc length, well, this time I'm thinking in terms of y. So my y values are ranging from 0 to 9, as we see over here. And since it's all in terms of y, this time let's factor out the dy squared term. So my length will be equal to y's running from 0 to 9 of factor out dy squared. So that leaves me with dx squared over dy squared plus 1 dy squared. All I've done is the exact same algebra I did on the previous one. I've just now factored out the y squared. And this becomes integral 0 to 9 of dx dy this time. Last time I had dy dx, this time I've got dx dy squared plus 1. And the dy squared comes out of the square root and is just a plain old dy. So the dy matches with my bounds being in terms of y. And I have already computed up above that dx dy is 1/2 y to the negative 1/2 squared plus 1 and then a dy. This is a very different looking integral than what I had in my previous step when it was y in terms of x. But this is just the same curve defined exactly the same way, so that ought to give the same value. We'll come back to that one in a second. Well, defining curves, I can write y's as functions of x's. I can write x as functions of y's. I could also do something parametrically. And just to do something really random, let's let y equals x squared. And I'm going to parameterize that curve by letting x equal natural log of t. I could let x equal anything I want to parameterize. I'm just going to go with natural log of t. All right. That means y, which is equal to x squared, is natural log of t squared. And if x used to go from 0 to 3, if x is 0, when is natural log equal to 0? Well, that happens at t equals 1. When is x equal to 3? Well, that happens at t equals e cubed. So then I could actually do my arc length running from t equals 1 to e cubed. But what do I do with my dx's and my dy's? The last couple times I could factor out a dx or factor out a dy because that's what I was in terms of. This time I'm in terms of t. So it might make more sense to actually factor out a dt. So I'm going to let my integral go from t equals 1 to e cubed. And this time I'm going to factor out a dt, dx squared dt squared plus dy squared dt squared dt squared, which becomes integral from 1 to e cubed of the square root of dx dt squared plus dy dt squared. And all of this is now an integral with respect to dt. Now dx dt and dy dt, those are easy enough to compute from what I had up here above. So if x is natural log of t, then dx dt is 1 over t, and dy dt, chain rule, is 2 natural log of t times 1 over t. And if I substitute both of those values back into this integral, then what I end up with is an integral from 1 to e cubed of the square root of dx dt squared plus dy dt, 2 natural log of t all over t squared dt's. Yet a third option for what this curve might actually be. And again, I'm going to put that on hold. We'll do a calculation of all of this at the end. And as a final look at this, what if we go into polar coordinates? So we can define functions x in terms of y in terms of x. We can define them parametrically. What if I define this thing polar? In polar, remember that the Cartesian polar conversions are x equals cosine of theta, x equals r cosine, y equals r sine of theta. And if I substitute those into my y equals x squared, I've got y equals x squared, so r squared cosine squared. And if I solve that for r, I get r equals sine of theta over cosine squared of theta. And looking in terms of my generic arc length formula, being the integral from some a to some b of square root of dx squared plus dy squared, and that's all I've got every single time. But this time, my function is in terms of theta. So I'm going to apply the exact same logic that I've applied every time. My function's in terms of a variable, so let me factor out the d, that variable. So when I factor out, I've got, skipping some of the intermediate algebra now, it's just dx d theta squared plus dy d theta squared. And I factored out a theta, so these are d thetas. And so now my bounds on my integral have to run on the thetas. Well, looking at y equals x squared over here on the left-hand side, that means my angles are running from 0, and this top order pair was 3, 9, which you can figure out is theta is arctan of 9/3, or just arctan of 3. And what I need to substitute in now is what is dx d theta, what is dy d theta. And that becomes a little bit more complicated. Polar is just a little bit more obnoxious in trying to compute the derivatives. Remember, my function is r equals sine over cosine squared. So then x equals r sine theta over cosine squared times cosine. X equals r cosine, which in this case just simplifies down to a tangent. Y is r cosine squared times sine of theta, which becomes a tangent squared, which tells me dx d theta is just secant squared from the tangent, and dy d theta is, from chain rule, 2 tangent secant squared. So now I know my dx d theta, my dy d theta, and I can take this integral that I had before, and I'm going to rewrite that as the length equals the integral from 0 to arctan of 3 of the square root of dx d theta squared plus dy d theta to tan theta secant squared theta squared all d theta. And this is a fourth way of apparently writing the arc length of y equals x squared from 0 to 3, and they all look really, really different. So let's transition over to a calculator and compute all of these. So what I've got here, I'm running this on a TI Inspire. You can run it on pretty much any calculator. I like the cast side of this just for the exact answers. But what we're looking at, and I've already preloaded all of my equations so I don't have to type them in while you're watching. We're looking at y equals x squared, and we're trying to go from 0 to 3. So the very first integral we had was in terms of x, and that was just an integral 0 to 3 of the dx, which happened to be 2x, dy dx, which is 2x squared plus 1. And we get a rather complicated looking expression. No big deal, not surprising that it's kind of complicated unless you've got a really nice line or part of a circle. Most of the time these expressions are just going to be ugly numbers. In terms of y, dx dy was 1/2 y to the negative 1/2, so we plug that in. Notice the bounds are now 0 to 9, and when I run the cast, I get exactly the same answer. I got a common denominator in the second one than I did in the first one, but I get the same answer both ways, so it doesn't matter which way I play this. What about our parametric version? All right, so parametrically, we had dx dt was 1 over t, dy dt was 2 log t over t, and our bounds are now going from 1 to e cubed, which gives exactly the same answer again. So it didn't matter whether I thought of the curve parametrically or in terms of x in terms of y, or if I thought it, parametrically, x in terms of y, y in terms of x, it's all the exact same curve. All right, and then the final one was kind of ugly, but that was our polar version, and our bounds were 0 to arctan of 3, and we just plugged in the same expression, and this time I get a numeric example, which if I come back up and grab the previous version, I'm getting exactly the same decimals. So what's in, one of the sidelights here is that it's interesting that the CAS computes these values in different ways. Notice it's slightly different formats depending on how I computed the arc length. But it's really simple here. Whenever you're trying to deal with finding an arc length, at its fundamental core, everything is always from A to B, whatever your bounds are, just depending on how the curve happens to be defined, and you're always doing the square root of dx squared plus dy squared. The arc length is adding up, that's all an integral does, adding up a whole bunch of little tiny Pythagorean theorems, and you factor out the differential that matches the way your function has currently been defined. I hope this helps.